now. Okay, all of us will go silent now.
Okay. Let's see, where is... Zoom. There it is. Yeah, share. Okay, can you guys see this?
Yeah. So Garimella, I was going to have
Yes.
instant coffee this morning, but I decided to grind it instead out of respect to you.
Thank you. Thank you. That makes my heart feel good. Okay. All right. As I had said before, heat transfer, without it, we'd all be dead. I mean, I hope you all are transferring some heat. Otherwise, you may not last too long. Same thing with this computer and just about everything around us. So this talk is kind of a survey of the various things in heat transfer that I do. We start with a little bit about actual heat transfer research, and then I'll move to some applications of that. So the name of my lab is the Sustainable Thermal Systems Lab, and this is kind of a schematic showing the kinds of things we do. Let's see, pointer options. So we look at a variety of heat sources like natural gas, solar, waste heat from a variety of sources, and then we put them through different types of processes, which is phase change heat transfer, which means either boiling or condensation, absorption, adsorption, and then we also do a little bit of electrochemical conversion. And these are the end users that we try to supply with the sort of overall overarching objective of decarbonization through sustainable thermal energy utilization. A lot of my research is in the utilization part of it. And for that, we need to understand heat and mass transfer. So that kind of sets up what we do. And to be able to do this research, these are some pictures from my lab. We have a fairly large lab, about a total of 5,000 square feet, where we have our own boiler, which supplies steam to various test stands. This is our wind tunnel that we can instrument and measure the temperatures, humidities, and control them. Can run it in once through or in recirculation mode for different experiments. These are the different steam stations. We have some environmental chambers where we can do controlled temperature testing of various equipment. Our own chiller, and then a very low temperature, minus 55 Celsius chiller. Those were the facilities, and here are some examples of the kinds of experiments we do. A lot of them have to do with providing the realistic conditions of actual processes. So you'll see some pressure vessels, you see a lot of instrumentation. This is where my condensation research goes on. This facility was built in 1995 with just modifications every now and then to address different experiments, different research topics. We have a lot of flow visualization that we do with high-speed cameras and so on. And then we test phenomena, heat transfer phenomena, as well as heat exchange components. And then we build full systems that incorporate some of those innovations. So I'll just have one equation in this entire presentation just to set the stage. The basic equation for heat transfer is that heat transferred is equal to something called a heat transfer coefficient times surface area times the delta T. Usually the delta T, or the temperature difference, is not within your hands. It's a process that someone else gives to you, and you have to try and within those temperature constraints transfer as much heat as possible. So you can either increase the surface area, which means more cost, or you can do something to the fluid flow processes to increase the heat transfer coefficient so that in the same area you can get more heat transfer, or you can cleverly arrange your components so that you use the available delta T better. And a lot of our research is in the micro scales. And the advantage of micro scales is that it offers both high heat transfer coefficients as well as large surface area to volume ratios. So the reason the heat transfer coefficients are high from a very, very simple point of view is that from the fluid to the wall to which it is transferring heat, the distance is very small. So if you go from, say, 25 millimeter diameter tube to a 1 millimeter diameter tube, the heat only has to travel, half a millimeter. So that's what basically increases the heat transfer coefficient. And then if you fit a lot of surface area into the volume because you have many, many channels, then you also get this high surface area to volume ratio. The other advantage is that the fluids that you're running, quite often they are expensive or they are corrosive or dangerous. When you go to these micro scale type of devices, you need less fluid, so it's less expensive. And even if there's a leak, the hazards are lower. So to be able to do this, we have to understand the fundamentals of phase change, heat and mass transfer. And so I'll spend a few slides on just the fundamentals of heat transfer, the research we do in that area. So these are flow visualization experiments on the actual condensation process in a very small tube, in tubes that are 500 microns in diameter and so on. This kind of research used to be done using simple air and water, just feed some mixture of air and water into a tube and watch it. But most of the fluids that are used in actual heat transfer equipment, they have very, very different properties from air and water. And also you are not doing heat transfer when you just send air and water. So we designed some very interesting tubes and so on, where we have the optical access, we can see that, and they can also withstand high temperatures and high pressures. And you can see that even though it is the same process of condensation, at the beginning there's a lot of vapor, and so the vapor kind of goes as a kind of a mist with a thin layer of liquid on the walls. And as condensation proceeds and you go towards more and more liquid, it becomes wavy, and then it just becomes like a slug. I mean, this looks like a garden hose, for example. And so you can also imagine that with this, the heat transfer behavior will be different in different regions of the condenser. So we pay a lot of attention to that and develop our models based on what we see in these flow patterns. So for example, I showed some bubbly flow in the previous one where there's a vapor bubble and then there's a liquid. And so instead of just brute force curve fitting, we try to develop a model for how the pressure drop happens in a bubble, and then what happens at the interface here and what happens in the liquid. So for example, the liquid, because it is denser for the same mass flow rate, it'll move slower than the vapor does. So there's a lot of sort of climbing over this and then coming down here. So there's a lot of shear that goes on here. So then we account for each of these contributions to the pressure drop. And once we know those, then we can come up with models. Whereas brute force curve fitting in the past used to lead to this kind of agreement between the measured and modeled values. Our models then get us much, much closer. And we've studied a wide range of tubes that are used in industry. If you open up your air conditioning system in your car, for example, the condenser tubes inside will look like these rectangular tubes with little triangular channels in them. So this helps with designing and optimizing these heat exchangers better. But it's not just one fluid. When you consider a variety of industries, just to study condensation, it can be in horizontal tubes, it can be in vertical tubes, it can be in microchannels with pure fluids, or it can be mixtures where there is fractional evaporation and condensation that's happening, and so on and so forth. And so you can't just apply the same techniques for this wide range of fluids. Ajay Pandey was talking about the different refrigerants that he's been playing with lately. So there's some refrigerants, synthetic refrigerants, there are hydrocarbons, there are mixtures of those two, and then there are these old refrigerants, ammonia, carbon dioxide, and so on. Each of these is a different fluid. And if you look at, from elementary thermodynamics that you studied 45 years ago, they are very, very different fluids. If you look at the vapor-liquid dome, for one fluid, like steam, it would look like this, whereas for another fluid, it looks much narrower and so on. And then the enthalpy of condensation. So when you go from vapor stage to liquid, at one pressure, there may be this much heat released. At another pressure, it may be much less. And also it changes as you go from one fluid to another and so on. So we have to devise methods that account for all of these. And the vapor to liquid or the liquid to vapor densities are very, very different. If you look at air, water is 845 times denser than air, whereas in an ammonia water mixture or ammonia, it's only about 35 difference. Surface tension is different and so on. So we've developed some versatile methods to look at all of these. This is, for example, hydrocarbons. This is how hydrocarbons flow in a refinery and so on. And each of these is two sets of movies. One is the actual movie that we took. The other is we digitize it using some MATLAB tools and so on. And then we are able to then see how much of the tube is occupied by vapor, how much by liquid, and that helps, and also how it changes with time. And so that helps us develop these models for these various processes. And then we've done some computational techniques to look at how condensation happens. So what you're watching is the progression from the vapor to the liquid. We're going down the tube in this case, and then it started with full vapor, and then it goes towards full liquid. And you'll see that the liquid is accumulating in the corners. This is good. This is why we use square tubes in some of the applications, because it thins out this area so that heat transfer can happen much, much better. The resistance, the heat doesn't have to flow through this thick liquid film, and it's able to transfer more heat that way. So for these, thousands and thousands of data points for a wide range of hydrocarbons, ammonia, CO2, and so on, we've developed models for these annular flows, wavy flows, intermittent flows, and so on, and got some pretty good agreement with that. Lately, there's a lot of attention in supercritical fluids. So a lot of the research used to be inside the vapor-liquid dome, but now both for power plants as well as for refrigeration and air conditioning, people are looking at this region. What happens here is, so you can imagine if a vapor comes and then it starts condensing and it becomes a mixture of vapor and liquid, and then here it becomes a liquid. Now here, that transition is happening without that phase change process. So what that does is, all of a sudden, if you look at the density, as you cool it down in supercritical conditions, it is changing from a very low density substance to a very high density substance without undergoing that phase change process. So then you see a spike in the specific heat. And so when you measure the heat transfer coefficients, they go through these peaks. And so again, through experiments and models, we have been able to capture that behavior. This is pressure drop. When the same substance is flowing as a gas, for the same mass flow rate, it'll be flowing at, say, 40, 50, 100, 1,000 times faster than the liquid. And all of a sudden, when it crosses that vapor-liquid dome, it plunges because its density suddenly increases, and then the pressure drop is much lower. So again, we've taken some very careful experiments and models and matched the experiments and the models. So this has helped us design supercritical systems also. So the other thing about condensation is that when the fluid enters as a vapor, it's moving very fast, and then some droplets of liquid start happening, and then there's shear between the liquid and the vapor. And that promotes heat transfer. So the heat transfer is very, very effective there. But as you go from this high quality region towards the end, it's mostly liquid. And then you can see these kind of stagnant areas. And here the heat transfer is very poor. And so you can have this much condensation happen in a small surface area, but then this little piece, this to go from say 15% down to 0% vapor fraction, this might end up being the longest part of the heat exchanger. So you have to do something to help this along. So recently we did some research where we've tried to disturb that vapor-liquid interface so that when there is more shear, there's better heat transfer between the liquid and the vapor. And so what we've done is we've done acoustic actuation, where we send acoustic waves, and then that pulsatile flow will disturb that vapor and make it behave as if there's a lot of shear. And then we have to fine-tune the frequencies and so on. I don't go into all those details. But for example, if this is the baseline flow without actuation, and that's the top view and the front view, with this actuation, it becomes much, much more agitated. And you can imagine that this will result in much better heat transfer. So that way we can reduce the size of the components by providing this fairly cheap actuation. One of the recent ideas that I came up with a few months ago is there's a lot of new attention being paid to AI, ML, artificial intelligence, and machine learning techniques. And then simultaneously, there are additive manufacturing techniques coming up. And so you saw in the previous slides that the fluid flow behavior changes as you go through the condenser, and also the heat transfer behavior changes. So is it possible to sort of tailor the diameters of the tube in a shell and tube heat exchanger so that initially when it is vapor, you provide larger diameter tubes, but then as you go down, you sort of scrunch down the size so that you're still getting approximately the same effective heat transfer, and thereby you can reduce the size of the heat exchanger. And then what you see here are what are known as baffles. There are baffles in every shell and tube heat exchanger, in every refinery, in every power plant, and so on. But we decided that we'll have hollow baffles so that once you've condensed a portion, condensed a portion of the liquid, it's doing you no good except providing some resistance to heat transfer. So we take that out, we draw it out. So with these, now the importance of additive manufacturing comes in because no conventional process can make these. But if we build these sort of increment by increment, aided by additive manufacturing, we can sort of tailor the heat exchanger to each application. So we've just applied for a patent for this, and we'll see how it goes. Okay, another research that I've talked to you guys about over the past few years is heat pumps. And my area of specialization is in thermally activated heat pumps. So I'll just give you a brief introduction to what they are. So this is the standard air conditioning system that Pandeyji fixed recently. Here you have your compressor. So how does an air conditioner work? You're trying to make heat go against its will. Heat wants to go from high temperature to low temperature, but you are trying to take the heat from inside the room and throw it out when it is 95 degrees F outside, and heat doesn't want to go that way. And you force it to do that by putting in a compressor. What the compressor does is it takes the refrigerant and pressurizes it to a high pressure, and at that high pressure, its saturation temperature is higher. And so from that higher temperature, it is able to dump the heat to the ambient, throw it away outside. And then you condense it and you bring it to a very low pressure. And when you bring it to a much lower pressure, this is colder now than the room that you're sitting in. So that room sends the heat into this and evaporates that fluid. And then it comes back to the compressor and finishes the cycle. The problem is that this requires electricity, and even today, a lot of the electricity is being made by fossil fuels with CO2 emissions and so on. And also, many of the refrigerants, the synthetic refrigerants that are available to do this, are being phased out. And so there's a big problem there. So the thermally activated heat pumps that I have been investigating for almost 40 years now, they use, instead of electricity, they use heat as the motive force. So basically, you take a mixture of two substances, and then you boil off using this external heat the refrigerant portion of it, and then that goes through the same process as in the conventional vapor compression heat pump. And then you mix it back into that dilute solution that was left over, and now you're pumping a liquid. And as you guys know, pumping a liquid takes, 1/100th of the electricity that you need for compressing a vapor. And so this is the advantage of this. And now there are a variety of heat sources. This can run on the waste heat. I'll show you some examples of that. It can run on solar energy and so on. And it uses natural fluids. You don't need the R134As and any of these synthetic fluids. So you're consuming much less electricity, and you have benign fluids and versatile heat sources to run this. But the downside is you took one compressor and then replaced it by 3 heat exchangers. So until recent years, this was prohibitively expensive and also large because you have many more components. And so one of the focus areas of my research has been to try and do this in compact envelopes. And so to be able to do that, again, you have to understand how fluids flow. This is sort of a shell and tube type of heat exchanger. These are called falling film heat exchangers, where you're flowing a liquid around a tube, and then you're cooling it by coolant flowing through this tube. And so for decades, the heat transfer modeling used to be done as if there's a well-behaved film, uniform film of liquid that flows around the tube, and then it just magically appears on the next tube and so on, not capturing all these waves and drops and so on that the actual heat exchanger has. So we embarked on a very detailed study of how the fluid actually flows. There's these filaments that are formed. They break up and form these small droplets. And then when they fall on this, there's a splash, there's a wave that's set up, and then the wave kind of spreads out sideways and sets up these saddle waves and then starts a new one. And then some of these droplets, because of surface tension, they don't merge into this fluid. So all of this affects the heat and mass transfer in these heat exchangers. And so we studied this in some great detail. And for absorption processes, here what you're trying to do is you're trying to absorb the refrigerant into this liquid. And so the surface area to volume ratio is very important. And so we digitized this, and we studied the progression of this interface with time. And there we are able to see how much surface area is there. And then we plot the evolution of that over time, and we are able to model the heat and mass transfer there. We also then did some computations. So this is CFD analysis on the right, and you can see that there's a pretty good match between what you see in an experiment and the CFD. So both spatially and temporally, we are able to capture this process quite well. So this helps us understand how to design these, because you can't just, with more fluid, a higher Reynolds number, you assume that you might get much more heat transfer, but it just coats the tube with thick layers of liquid, which provide big resistances, and that's not good. And so this helps us as a design tool. So with all these kinds of insights, here are some rectangular tubes. And again, it's not just enough to have fluid flowing over tubes, it has to wet the tube. So here, there are these dry patches which are doing us no good. So we have to understand how to feed the fluid to these tubes, and that'll help us design these systems better. So here's another example of how to distribute the fluid on these tubes, different types of feeders, and they give you different flow patterns here. So then we've analyzed these and tried to figure out how effective they are. And then these are heat transfer experiments. So there's coolant flowing through these tubes, and then this absorption process happening on the top. Now you can see that when it falls here, hot fluid starts cooling down because its heat is going in there, and then a new interface starts. So this is a fully spatially 3D resolved as well as temporally resolved heat transfer process that helps us design these systems. So now that's this is the work of Girish, who's attending this. One other way to enhance this very simply is to throw in a little bit of surfactant. Surfactant is nothing different from something like your soap. And you throw that in and you get much more disturbed interfaces, which gives you much better heat and mass transfer for very, very little investment. So this is other ways in which we try to help the process along. So with these insights, we designed many years ago a system, an absorption heat pump system that I showed you the schematic of before. This is just 5 inches by 5 inches by about 14 inches. And essentially, you use the advantages of microscale tubes. So you send tubes through, you send coupling fluid, cooling water or something through the tubes, and then you pour the liquid on top, and it goes through that evolution that I showed you before, and you send vapor from below. That vapor gets absorbed. The heat of absorption gets sent into the tubes. And so this does the absorption. But the beauty of this is by just changing it a little bit and flowing hot fluid through this, you are able to evaporate that vapor too. So the same component with just a change in the tray at the top also functions as a desorber, and the same component can function as an evaporator and a condenser, the 4 components required for an absorption heat pump. So there's a lot of uniformity in the components, which helps in the manufacturing costs. So this is a 3-ton, a typical household refrigeration system that 4 of these things will do it for you. But after that, about 10 years ago, we thought, well, we want to make it even more compact. So this was one of my PhD students' dissertation work. And the challenge I gave to him was build a heat pump, build an entire heat pump, the size of the heat transfer textbook that we use in our coursework. And he built it. In fact, it's a little smaller than that. And the way we did that is we took these thin sheets, 0.5 millimeters thin stainless steel sheets. We etched these passages, 250 micron passages into this. And the fluid kind of travels. So this is the actual cycle. The fluid is boiled here, it is purified here, it is condensed here, it goes through a recuperative heat exchanger, then evaporates, absorbs, and solution heat exchange here. And so you take pairs of these sheets and then slap them together, put a cover over it, and that forms the heat exchanger. So this thing is the entire heat pump. It's not just one component. So through the advantages of microscale, as well as integrating multiple components into one monolith, we were able to transfer something like 350 watts here using waste heat, for example. So then we pitched this to the government, and they gave us a lot of funding to scale it up and so on. And then we built a series of products like this. This is a air conditioning system that we built that is able to use just waste heat or solar heat or something like that to provide cooling at ambient temperatures as high as 52 Celsius. So in the Iraq war, in the battlefields in Afghanistan, and in some regions of India now, I guess, you're facing these kinds of temperatures. So this is ready to handle that. We also developed, so these were built using diffusion bonding and chemical etching. And then we came up with simpler, cheaper ways to do this, stamping, and then brazing these together instead of diffusion bonding. And then this one was the one actually for the battlefields where the diesel engines, so taking diesel to the battlefield is very, very expensive. So the diesel is used to provide on-site electricity, and there's a lot of waste heat. So we used that waste heat to run our absorption heat pump and thereby achieved more bang for the buck. So it was producing electricity, and then the waste heat was being used to cool the tents and so on for the soldiers or some sensitive equipment. This is a heat pump water heater. So there are electric heat pump water heaters, but this is a gas-fired water heater. So when you burn gas to heat your water, at best it'll be 100% efficient, more like 94, 90, 95%. Here, you are using that heat to run an absorption heat pump, and it can give you, for every BTU or every joule that you put in, it'll give you about 1.7 joules because it is pumping the heat from the ambient also. So this was another PhD student's dissertation where this is the household water heater. This is in my basement, and the basement height, ceiling height is limited. So the challenge was to fit that whole absorption heat pump within this space, and he was able to build it. And so those are some examples of absorption heat pumps for space conditioning as well as water heating using heat as the source. Now, this still needs a little pump, right? I mentioned that you need to pump the liquid. What if you don't have pumps and you're in some remote area in developing countries and so on? Well, how about we get rid of the pump also? So we came up with this system where the bubble, as it is rising because of buoyancy, can pull some of that liquid up. And so this is the bubble pump that runs the whole cycle. And so this was just a schematic. This is PowerPoint engineering, but then we actually ran this and we did some high-speed photography. We did some dynamic image analysis, and then we matched it with CFD to be able to develop completely passive system that it can be used for transporting vaccines and so on in sub-Saharan Africa and so on. So that's another example of that. And then this is at the other extreme. If you look at naval warships and so on, some of these big aircraft carriers and so on have 300 megawatts of heat going in, and then to produce the electricity and so on. And so there's 200 megawatts of waste heat available. And so we decided that we could run an absorption system to provide, say, 5 Celsius type of cooling for cabin cooling of the ship and so on. And then they have very advanced weaponry and so on. And then we use that as the heat sink rather than the 95 Fahrenheit heat sink. And we put in a little electricity to run a vapor compression system. We cascade the vapor compression system with the absorption system. And we were able to then provide, using this 200 megawatts of waste heat, about 90 megawatts of cooling at 5 Celsius plus 50 megawatts of cooling at minus 40 Celsius to cool the advanced weaponry and so on and so forth, using just a little bit of electricity. And then we used our microchannel expertise to have condensation happen in these very thin channels, and then the falling films on the outside to really scrunch down the components. 40 megawatts can be transferred across just a temperature difference of 3 Celsius in a fairly small array. Okay, about 5 or 6 years ago, one of the largest companies, commercial laundry companies in the world came to us and said, our dryers are wasting a lot of energy. 55% of the clothes drying energy is just being wasted. Can you do something about it? Well, we did some clothes pore level analysis. Then we looked at the heat transfer, mass transfer of moisture in the textiles. We saw how this moves in the actual dryer in the tumbler, and then we developed system level models. And so in an actual dryer, this is the temperature profile with time that happens. Initially, the clothes have to be heated to the evaporation temperature. Then the moisture starts evaporating. And then that's not enough because there's moisture deep in the clothes. And so you have to heat it even much higher than the saturation temperature. And then there's another phase where you're drawing out the moisture from deep inside the clothes. And then there's a cooling cycle. So here we saw a potential for waste heat recovery. So this portion doesn't need that much heat or that much high temperature heat, whereas this one produces a lot of high temperature. So we thought the exhaust from this can be used to feed this and so on. So we came up with different energy savings potential. So some recirculation of that hot air back to the inlet, but then you have to do this judiciously because it's hot and wet, and you can't put that back into the clothes because you're trying to dry the clothes. And so we did some recuperation, and then we took that hot, moist air coming out of the dryer and put some silica gel or some other adsorbent into the dryer. We squeezed out all the moisture, and that hot air that was left, we sent it back so that we didn't have to heat ambient air that much. And then we also put in an adsorption heat pump in there. So these are some of the potential energy savings that were possible with it. And we actually, this is our lab. We had a commercial dryer here, and then we fit all of this additional equipment into what was empty space here. So that allowed us to reduce the energy consumption by about 22%, and also reduce drying time, because commercial laundry's time is important too. We reduce the drying time also by approximately that amount. A very different application. There's carbon capture is a hot topic these days, and we developed some techniques to do CO2 capture from coal-fired power plants. So basically, these are hollow fibers that are about 300 microns in diameter, and then there's a matrix outside with these adsorbent crystals embedded in them. And so the flue gas from the power plant is sent over this, and these crystals will adsorb the CO2, and that heat of adsorption is taken away by coolant flowing through these tubes. So this is how the process happens. Flue gas flows, and the heat of adsorption is taken away. And then the captured CO2, then later in a second phase, you send some hot fluid through it, and the CO2 is evolved, and then you collect it in drums and then sequester it. So that's the overall process. But you can see that there's some heat transfer required. You don't want to burn new fossil fuels to be able to capture this. So we devised some clever recuperation techniques, and I'll show you that in the next slide, where you saw that there's a thermal wave that is going through, and so that thermal wave is being sent. So you're chasing that, and my mouse stopped working just a second. There. So you're chasing this wave so that you pick up the heat from that hot, the heated coolant, and then you save it for the next phase. So the additional heat that you need is very little. So we were able to achieve pretty high product purity, and thereby capture the CO2 with very little energy consumption. Now, in an ongoing project, we are working on heat pumps with integrated thermochemical storage. So I've been talking about this in our group for some time now. There's a big push to make everything heat pumps. Well, if in the peak winter you want everything to be run by electricity, there isn't all that much electricity there, and all of a sudden the peak electricity demand happens in the winter. So can you do something about that with thermochemical storage? And so we said, well, here's a conventional vapor compression system, vapor compression heat pump. And then you take the condenser reject heat and you put it into an adsorbent bed. You charge it at times of low demand. And then you put in this evaporator. So you're charging this. And what that means is you're getting rid of the water in this thermochemical material, and so now it is dry, and so it is ready to absorb heat and then give out the heat in the next cycle. That's what you do when you need that heat. So you're basically taking low demand periods and storing that heat and then using it later, so that you don't need to build new power plants. And if BS is listening here, your Cancun guy, the senator, doesn't have to run away because your electricity demand will not be as high, your grid won't break. So then we developed this system, and then we modeled the charging phase, the storage phase, and the discharge phase, and shown the merit of doing this. Another area of research, I'm not doing this anymore, but this was something we looked at before. Electric vehicles are very popular these days, but the thermal management problem is a significant problem. And I guess Balsara can talk about this much more than I can, but what happens is that there is always waste heat when you're charging or discharging a battery. And it's not a lot of waste heat, but the materials out of which the batteries are made are almost perfect insulators. So huge thermal gradients are set up. And almost all battery cooling techniques to date are ones that kind of blow some hot air or some cold air on the surface of the battery, or at best put some cooling jackets around them. But what that does is it might cool the skin of the battery, but then it creates this temperature profile, which is terrible because the discharge and charge depends on temperature profiles. There is a differential charging and discharging. And so the battery stops discharging or charging when it sees this profile. So when one portion of it is charged, it thinks that the whole thing is charged, and then it stops, or vice versa for discharge. And also, this is the kind of profile that sets up differential corrosion and so on and so forth. But you don't want that. So we came up with this idea of integrating these small microscale passages in the current collectors themselves, and then charging it with a little bit of refrigerant. And what this does is passively, due to buoyancy, when there is heat generated, it sends the vapor up, and then you blow air over these finned surfaces on the top, and then it condenses and it just goes back passively. So it's a thermosiphon type of thing. And with that, you're able to achieve even temperatures, thereby increasing the life of the battery as well as the depth of discharge, how much charging and discharging you can do for the same amount of material. We also studied the thermal runaway. If there's a short circuit, internal short circuit or something like that, then this thing goes pretty fast. I mean, the thermal runaway can happen within a few seconds. And so we studied this so that we can come up with some signals to alert of this possibility. And temperatures can reach the thermal runaway temperatures even within 15 seconds. So this is some research we have done, and you can see that it can suddenly reach something as high as that, as 262, and then there's these fires that you hear about in the news. Okay, this is, I don't know if Anurag is on or not, but this is a collaboration between his company and our lab. And basically, he does some fantastic work where he's taking local biomass and then using an adsorbent bed to provide adsorption cooling for extending the shelf life of vegetables, fruit, milk, and so on and so forth. This is a system that his company provides. And this is a huge problem because obviously there's a lot of agriculture produced in India, but the farmer, when he goes to sell it in the sabji mandi, it is a very limited shelf life. If you can extend it even by a few hours, a lot of wastage can be avoided. But as you all know, electricity supply is not very reliable, and also just, if you have compressors and so on, and something breaks and out in the field, they don't know how to fix it. So this is a completely, very passive type of system with very few moving parts. And the bed material uses chemisorption instead of physisorption. And chemisorption leads to stronger bonds, therefore it can store larger heats of adsorption. So per unit mass, you can handle much more of the cooling load. But there are not very good models out there in the literature. So we are helping him by sort of modeling the adsorption process much more carefully, also designing condensers and evaporators to be more compact. And he's been implementing some of these in his systems. So he takes this biomass and a wide range of substances. He's using things like coconut shells, twigs and gobar and all of that to whatever is available to produce the heat. And then we run an adsorption, two-bed adsorption cycle where this will remove the refrigerant from here. This provides the condensation, and then you have the evaporation to cool sheds. This is the shed in which you store the fruits and vegetables. And so using this biomass gasifier and this thermally driven chiller, you can provide cooling. And so this has these, you're using the agricultural waste for some useful purpose. The carbon footprint is zero because this is biomass. And then you are combating food spoilage and also reducing air pollution. I have just a few more things to say, and then we'll open it up for discussion. One of the projects that one of my students did in about 3 or 4 years ago is we are doing this absorption cooling anyway. And households have a lot of waste water when you wash your dishes, when you take showers and so on. You're taking clean water and then you're just draining out this gray water, what's called gray water, and there's a severe water shortage these days. So since in a standard absorption cycle, you are going through this double distillation process anyway, because here you're evaporating, and when you evaporate, pure water comes out. And then again, when you're desorbing, pure water comes out. So we broke the absorption, the closed absorption cycle, and we just opened it up and said, okay, water, do the cooling for the house. So this is the space conditioning. And then in the process, get purified. And then you're able to take that gray water and make it pure water, not potable water, but cleaner water. And we actually built this system and demonstrated that we can do this. So it's two end users for the same input energy. We're working with Novelis, which is part of Hindalco, the Indian company. And these large aluminum ingots, when you're casting them, the way the ingots are formed is this molten aluminum is poured in, literally. And then you send cooling water on the sides. And when you send cooling water, it evaporates, and there's a lot of water that evaporates and just goes away to the outside. And then we have cooling towers and so on. But these days, people are paying a lot of attention to water wastage. And so we wanted to find ways to reduce energy and water consumption, especially because this is treated water. And once you've treated the water, you want to make use of it and not just keep dumping it. And I mean, there's a lot of water that is lost in this casting process. And so we first developed some very careful models for this. This is the actual transient cooling process. So this is the ingot that is formed, and then due to this cooling water, this outside cools down, and then slowly that front propagates inside. We calculated the amount of water vapor that is generated, and then we suggested some ways to condense that water vapor again so that it goes back into the pool and can be reused. So we have come up with this technique to do that. The other project we're working on right now is, I don't think there's too much drywall in India, but here a lot of the buildings, almost all the buildings have drywall. It's called drywall, it's called sheetrock. It's basically stucco, gypsum, stucco, that kind of thing. The way that is made is it is calcium sulfate with some water, and you heat it using fossil fuels. You send hot gases over it to calcine it, and then it is formed into a slurry, and then you have to dry that slurry. And so it's a lot of energy and a lot of water that is consumed. But when you're sending this hot gas, well, first of all, the hot gas goes into this thing, and then it leaves as less hot gas, but still it is very, very hot. So you're just throwing away a lot of energy. On top of that, this is convective and radiative processes. Therefore, there is an inherent temperature difference across this mass that you're trying to calcine. And so the product uniformity is not there. So to avoid all of this, we came up with using electromagnetic radiation. So we are actually sending radio frequency waves through this material to heat it up uniformly from inside, from internal heating. And so there's no flue gases, there is no waste heat that is being produced. And because it is internal heating, it is inherently uniform. And so we've been doing this. We take these little samples and we heat them using RF heating. And first the free moisture is removed and then the calcination is happening. And we can actually see that there's 63% energy and 50% water savings. And this is a huge, huge energy intensive industry. And so the prospects are very good for significant savings. This is the student that I talked about who defended earlier this week. So in power plants, as you know, they need cooling towers. And when you need cooling towers, you are wasting a lot of water. So power plants consume an enormous amount of water. And so we were trying to see if we can reduce cooling tower usage. And the advantage of cooling towers is that you're not just using heat transfer, you're evaporating the water, and therefore that heat of evaporation is helping you. But it consumes water. So we said, okay, let's take a typical condenser and try to enhance the air side. So we put these little plastic sheets, little flags, in the fins between or between the fins of the heat exchanger. And what that does is just when you blow the air over it, it starts fluttering. And this fluttering motion will help in disturbing the boundary layers and increasing the heat transfer coefficient. And this is how the fluid moves and causes these vortices to be set up, which enhances the heat transfer. And this can increase the amount of heat transfer that is possible, approaching what is there in cooling towers, thereby reducing the water consumption. And I think this is my last topic. We also do a lot of research on nuclear reactors. And light water reactors, one of the sort of hazards there is that you're taking the primary coolant and then you're sending it to a secondary heat exchanger to generate the steam in a separate envelope. And so whenever you have separate envelopes, then the possibility of breakage, leakage, and all of that is more. So we said, well, why don't we put, so this is the nuclear reactor core housing. The reactor is in here. And then you surround it by these microchannel heat exchangers so that the primary coolant exchanges heat with the secondary coolant inside the pressure vessel, so that if there is some accident or something, it is all contained inside this pressure vessel. So that was an innovation we came up with. Another class of reactors is high temperature gas reactors, and these are being considered seriously because they produce power. And they also have the potential for generating hydrogen, which can be used for other processes. And so we have done some detailed thermal hydraulics and neutronics analysis, so coupled neutronics and thermal hydraulics analysis. But these are very, very painfully computationally intensive. So we've come up with some sort of computational shortcuts to still capture the phenomena, but be able to analyze these across the entire core. In a nuclear reactor, heat generation is not uniform. So there's a radial peaking of the power because of how the neutron flux is, and there's also an axial peaking. And there are reflectors, there are control rods, and so on and so forth. So it's not a homogeneous domain. And so we came up with these analyses to predict what happens to the coolant, what happens to the graphite moderator, and so on and so forth. And these are the temperature profiles that we've calculated in steady state. But then we also did accident scenarios. If there is a loss of coolant accident, then how does the cooling happen? Well, initially the temperature jumps and then it goes down. And then it climbs up, and then so we've modeled this entire process through many hours to see whether it'll exceed any sort of danger point. So initially there is the heat generation is there, and then it goes down, and then the power removal and so on. So we've traced that. There are small modular advanced temperatures reactors of that same nature. Again, other sort of transient temperature profiles so CFD analysis can be done on small sections, but our contribution was that without doing CFD, with some careful sort of reduced order models, we modeled this entire sort of combination of fuel and graphite and so on. And then we were able to predict the transients too without needing massive computational power. I think this is the last slide, but so this is another idea that we came up with. We applied for a patent for this. Molten salt reactors are coming into the fore because they don't need high pressure. These are ambient pressure, so your pressure vessel cost goes down. But also the fuel and the coolant is the same. So it's the fuel and the coolant that is moving around. And so we came up with a natural convection idea for doing the cooling so that there's no pumping required at all. So it's automatically natural convection. And what we did is we raised the cooling system up so that there's a buoyancy force that is set up, and natural circulation is what takes care of the cooling in case there is some accident or something like that. And we were guided by the size of a semi-truck. This thing can be put in a semi-truck and transported by road. So that it's a 200 megawatt thermal cooling system for a reactor. Okay, I couldn't do any of this without the help of all my students, and these students are at a variety of places these days. Several of them are in academia, some of them are in major corporations, some have started their own companies or working for smaller companies, some are working for national labs and so on. And this is my current crop of students. We took this picture just 3 or 4 days ago. And this is a humorous take on what we do.
No women in your group, or maybe the picture is too small, I can't see it, or most of them graduated already?
No, there's one woman here.
Yeah, okay, got it.
Yeah.
Okay.
Okay, it's open for questions now.
So, Garimella, you've seen there's a lot of mathematical modeling involved in what you're doing here, at least from I saw from the initial slide.
Yeah.
So to what extent, how accurate are those models in terms of reflection of reality? Because you are making kind of decisions or designs based on those models. So I kind of missed the part where you of how you're measuring the accuracy of the model, or how reflective are they of the actual situation?
Yeah, that's an excellent question. My work actually, I would say, is probably 75% experimental and 25% computational. And for every computational model that we do, we have experimental validation. And often it goes the other way. We run the experiments, we get the results, and then we come up with models based on that. So, and we reject any model that cannot predict it within a certain error band and so on and so forth. So it is also pretty difficult to get papers accepted these days without that validation step. And especially for these nuclear reactor things, it is, it's a very, very strict regimen of validation that has to be done to ensure that the models are indeed predicting the phenomena properly.
So are there like standards or a model validation requirements or standards which people look at for accepting something? Are those quantified?
Yeah, let me stop sharing so that we can see each other. That's a very good question. There's an entire there's an entire field of engineering which is validation, and there are benchmarks. So every computational model that you have, any code that you come up with, there are certain canonical problems you have to solve and show that it is matching those. And then and only then are you allowed to use your model to predict these new things. So that is very much there. You cannot publish, you cannot get things accepted without doing that step.
Okay.
Hey, Gary, brilliant work, man. One question on the, one question I had for the nuclear reactor industry. Has there been any massive change in terms of the design in recent years?
Yes. So, for example, the nuclear industry was pretty much dead for almost 30 years. Dead meaning no new nuclear reactors were being made, and they were just extending the old reactors and so on. The trend in recent years has been to move to smaller and smaller modular reactors, and they are being implemented. And then these newer molten salt reactors, and so Bill Gates funded some very interesting. There's TerraPower. There's a few other companies. There's one that is being commissioned in Wyoming, and so these are different fuels, different coolants, different cooling systems. There is not one yet that has been commercially implemented, but it is under construction now, which is a huge step. And one of the advantages of these newer systems is that they can be licensed at the factory. One of the biggest hurdles in implementing nuclear power for many, many years has been that each site has to be licensed independently. And so that caused all kinds of delays, public comment, all of that. I mean, you would spend 10, 15 years just dealing with that stuff. So now with this sort of modular nature where you can put this thing on a truck and transport it and just kind of install it, that has reduced that delay. So the one in Wyoming that was initially funded by Bill Gates, it's a molten salt reactor, and that is the sort of the standard bearer. That's the trailblazer in these new types of reactors.
Okay.
We also had in near me, there's a plant called Vogel plant that Southern Company, Georgia Power, built. It's like 1,200 megawatts or something like that. It's still the old one, but it's a revised design of a light water reactor. That still is a pressurized light water reactor, but it's an advanced design of that. So nuclear power is coming back, I would say.
Gary, what are the other research areas which other universities are doing? So that is question number one. Question number two, how good or bad is IITK vis-a-vis the heat research and all that?
Let me take the second question first. As you know, I visited IITK, I think 2 years ago, and was on the evaluation committee for assessing their programs. IITK still holds on to some pretty good strengths. I think there's a distinct difference between the IITK faculty and other faculty that I've seen, whether it is IIT Delhi or some of the newer ones. We can forget about the newer ones. Those are not anywhere near. I think there are some very bright people at IIT Kanpur. They also have a lot of money. But I think there is a culture there where the student to faculty member interaction, they don't give enough ownership to the student, and therefore then they don't expect as much out of the student. And so the student is just conducting work based on instructions. I think there are some very bright guys. Unfortunately, one guy died a few months ago. Samir Khandekar. He was actually very good in heat pipes. And I got to know him well. He was a good person as well, a very well-known researcher. There's another guy called Muralidhar. He's very good. There's pockets of excellence there. There are some entrepreneurs. There's a guy who does a lot of engine research. So just like with any other place, there are some guys that are very good, but then that culture of research is still in its infancy stages. Now, regarding the other question about what are the other universities doing, I mean, the sky is the limit in terms of what others are doing. I guess I would put the answer slightly differently. I think the research that my group does differs in the way that we don't just stop at fundamentals. Most other research labs will do benchtop experiments. They will do, they'll take a gram or two of some substance and measure its properties and so on. I usually start the opposite way. I look at an actual application and then try to solve it. And then in the process, I discover the need for some fundamentals to be investigated. And then I look at that. I guess these days, unfortunately, both in India as well as here, as well as everywhere, the new buzzword of AI ML has just infiltrated every single university. And they just, the expression I hate the most is, let's throw some AI ML at it. And it's a disaster. So that's happening. Thermal storage is a very hot topic these days. Everyone is clamoring to do that. We have been doing that for many years, but now it has become fashionable. Yeah, I mean, I don't know what else to say. There's research in all kinds of areas. Materials and heat transfer combination. That's a good subject. The research is all at the interfaces of fields. You can't just be a heat transfer engineer now. You have to be a heat transfer, fluid mechanics, thermodynamics, manufacturing, and materials engineer. That's what is leading to the new solutions. I think Sundarajan, you had a question?
Yeah, I had a question. Yeah, go ahead, Sundaraj.
Yeah, Srinivas, is a very fantastic presentation, a very smooth and very good delivery of whatever you have told us. I understood a lot of things, not as much as what you know. I just want one simple answer. You talked of power plant cooling towers, and you said some additional fluttering thing you have put somewhere, and therefore it increases the heat transfer and reduces the water consumption. So I am aware that the net water consumption based on the circulating flows is about 3%, 2%. It starts reducing. So with this arrangement, what is the design? How much it will come down to? What percentage it will come down to?
Yeah, that's a very good question. So there's a nuanced answer to that. It's not just a binary solution. What happens is that you don't need to be running the system all the time. There are peak times when you can still throw in a little bit of moisture to address that very hot day, but through the rest of the year you can run this kind of a system, and you can reduce this. So so far the solution that we have come up with will not get rid of cooling towers entirely, but it will reduce their usage. So I would say the degree of enhancement we have been able to achieve will lead to, I can state it more in terms of energy efficiency, about 1% or so of the power plant efficiency, without water consumption. So it's always an energy and water nexus, right? But a 1% improvement in power plant efficiency is very, very significant when the investment here is fairly small.
Okay.
GS, can you look at the chat box and provide the answers? Those guys have asked these questions long time back.
Let's see what.
I had one, Gary, if I may.
Yeah.
Firstly, I want to congratulate you because most of the people, I was involved in a lot of CFD work in my So CFD is easy to do, and then do 1 or 2 experiments and publish a paper. But we have done the other way, which is excellent actually, because you have a lot of capex involved in setting up lab. But one specific question I had was on the battery thermal management you're doing. Is it restricted to 12-volt battery, or is it generic to any battery?
No, it is generic to any battery. The problem in implementing that is there used to be a company called A123, which became very, very famous about during the Obama time. And they were so busy manufacturing the batteries that they didn't want to give us access to the internals of the battery. No company wants you to fiddle with the insides of their product, because then you can screw it up. So the resistance comes from people not wanting to work in an integrated fashion between the cooling and the actual process. This is the same problem that the entire electronics cooling industry faces also. All these damn chip makers will just make a chip and say heat transfer is your problem, and then then they complain when the processor slows down. I think Woodruff knows this quite well. So it's the same thing about batteries. That the solution that I mentioned can be applied both to these prismatic batteries as well as the jelly roll. If you look at your typical AA battery or AAA battery, it's a jelly roll. And you can use it in those too. So that's the answer to that. Let me see if I can get to these questions here on the chat, and then we'll ask. Let's see, Pradeep Gulati, heat pumps in air conditioning, how much time for them to replace conventional air conditioning system? So one misconception that I want to correct is a heat pump is not any better than an air conditioning system for air conditioning. A heat pump will do nothing for air conditioning. It is the same thing as an air conditioner. Where the heat pump is being pushed in countries like the US and in Europe is that it is a heating solution. It can be a heating solution so that you're not burning gas or some fossil fuel for doing the heating. So, and also the advantage is that then you're only building one system, right? So you don't need a furnace and you don't need an air conditioner on top of that. But in India, for example, the benefit of the heat pump is a little more elusive, because you guys don't need, well, in Delhi and Kanpur and so on, you do need some heating. But so I hope I answered that question. Let's see. Genetic algorithm, we are using our own various random forests and so on and so forth, the physics informed networks. We write these in Python, and that's what we've used for developing that geometry that I showed you for the AIML and additive manufacturing condenser. Okay, I answered the question by Subodh. Fluid flow packages and verified it. I think that's a comment more so than a question. My question is to Vivek.
Same question. I verbalized it. Okay.
Okay. Yeah. What else? Any other questions?
I had a question about the heat pumps again, kind of along the lines of what I think was asking before. Why haven't they become more popularized become mainstream in the US? Is it because of the cost? Is it because of they're applicable only in certain climates like California? Or is there a reason why something like this has not been more popular? Because I guess the concept of the technology has been around for a while, but it's not popular and it's not mainstream. Why is that? What do you think is the reason for that?
Two main reasons. One is that the CO2 emissions and climate change have not been a big driver until now. The other is energy is still very, very cheap in the US. Compared to any other country, energy is very, very cheap. And the capital cost of a heat pump is much, much higher than of an air conditioning system. And part of the resistance is more how the business is run, you probably know that when you build a new community in the US, it's the builder, it's the developer that controls what equipment is put in there. And they put all their money into the sort of the external features, the cosmetic aspects. They put in the cheapest possible air conditioning system, the lowest seasonal efficiency rating air conditioner in the house. And if you want to buy the next one, it's a significant cost premium. But they're coming. I think incentives will help. And then you also mentioned, is it a good solution? Well, the answer is not uniform. In California, it will work wonderfully, but then in California, you don't need it that much. In Atlanta, it's not so bad. It'll work quite well. But in Chicago, it's not such a great idea because the heat pump has to take heat from the outside when it is, minus 25 degrees and pump it into the temperature inside the room, which is, 72 degrees or something like that. And the compressor has to work much harder to pull heat from that colder temperature and put it into the house. And so its efficiency, the efficiency of the heat pump, there's a certain point where it's only as good as one. I mean, so it's you're just putting in 1 joule of heat and you're getting 1 joule of heat. So it's not good for that climate. But there's a lot of recent research that is going on in places like Purdue University and also outside on high lift heat pumps. So they're trying to build. So the way to build a compressor that can handle that is a 2-stage compressor. But when you see the price tag, you're not even interested in buying a single-stage variable speed heat pump. So to convince someone to buy a 2-stage heat pump is quite a challenge. So cost is important. And then in the very, very cold climates, the heat pump still is not the right solution.
So in California, the large building houses, or rather the mass-built houses, they are putting heat pumps in more often than not for overall efficiency purposes. That's built into the thing. So even though they're commercially built, but people individually have not moved to heat pumps as much as let's say the builders have. The builders are ahead of the game on that.
Yeah, I mean, you and Chetwani and I talked about this often, and the heating load in California is not that significant, right? I mean, how often do you need heating in California?
San Francisco you do, but not in other parts of California.
So in LA, it makes no sense. I mean, it'll work well, but you're spending so little in heating that the efficiency gain is not going to result in dollars saved. And once again, I want to emphasize that a heat pump is only as good as an air conditioning system for cooling.
Yeah.
Hey, Gary, I have a question. Nice talk. So, there are a lot of many old heat exchangers lying around, decades old. So I assume these pipes get rusted, get holes, whatever. So is there how do people monitor it? How do they know that, bad things are happening, right? I mean, some efficiency drop is always there. But what are the effects of rust or holes in the pipe?
Yeah, so in large chemical processing industries, power plants, and so on, there are ways to plug individual tubes of a shell and tube heat exchanger and keep going. And the design safety factor allows for some fraction of tubes to be plugged or something of that nature. The category of losses you are talking is also something called fouling. It's not just rust. If you have a kettle at home, you will see that as time goes on, it develops that white deposit of mineral deposits, and that presents a very huge thermal resistance to that heat transfer process. And so in industrial heat exchangers that undergo fouling, there are maintenance schedules. So every 6 months, they have a program where they send something akin to a detergent to clean that off.
Calcium chloride or something. Is it?
Yeah, it depends on which service it is. Depending on which chemical is the regular fluid that's going through, what deposits they come up with that. There are also literally brushes that you can send through, just like you're sending fluid through, you can send brushes through these tubes and just kind of scrape off that fouling. So, and then another class is diesel. Diesel fuel-based heat exchangers. There's this soot deposit that is formed, and the people can use some vibration techniques and so on. But the good thing about that kind of fouling is that there are mitigating circumstances. Initially, the fouling will form, and then there is a steady layer, and then there's a shedding mechanism that comes into play, so the soot layer doesn't go beyond a certain value, and so that you build that into the design. We are actually doing a project with Carrier Corporation for industrial chillers, where we are actually accounting for this. So an industrial chiller has a lifetime of approximately 25 years. And the chiller is designed and built in the lab. It is tested in the lab before it is sent out. But the chillers can go to Norway, they can go to Malaysia, they can go to Saudi Arabia, and so on. They function in very, very different service. And the quality of the cooling water that's provided to them, the quality of dust and all of that changes. And so the performance is not as designed. But it's not a lab in an actual installation, so you cannot have all kinds of instrumentation and flow meters and all of that to monitor this over the years. So we are, as we speak, we are developing methods to take very few measurements with a thermocouple, a power meter, and so on, and then interpret what is going on in the compressor, interpret what is going on in the fouled heat exchanger, and so on, so that we can come up with these mitigating techniques.
Thanks, Gary.
Let me add something. In heat exchangers, he's talking of small holes in tubes and other things. So Srinivas already explained anti-fouling mechanism and what can be done. And there are a lot of anti-foulants that are being used in various exchangers. But if there is a small leak, depends on the fluid on both sides of the exchanger, both sides of the tube and shell. It can create a loss, it can create an environment problem, and it can be like, suppose you have LPG on one side being cooled, and if it leaks, definitely LPG is much higher pressure than the cooling water. So it goes into the cooling water, it can go to the cooling tower, and it can form explosion. And if some work is going on there, in fact, in 2014 or 15 in HPCL Vizag, some 30 people died because of an explosion because of LPG coming there through the cooling tower, through the exchanger, because of leak. It could be dramatic depending on what fluid is being processed.
Thanks, PK. That's scary with this old stuff. Yeah.
Sap?
Yeah. I could gather some of the talk, but I got no questions for you. So great. Thanks, GS.
It's a good presentation, Srinivas. It covers a lot of different ground, and I again like the more value-added approach as opposed to the populist approach on research. That's really good.
Thank you.
Yeah, definitely more practical and kind of also makes a business case, So
Yeah, Vivek has something to say in answer to Arul's question.
Yeah, great.
Vivek,
Why doesn't
Yeah.
he? Why
Vivek,
doesn't
why don't
he?
you just unmute and talk?
You should unmute and speak up.
I did not expect to be put on the spot, but I'll give my best kind of summary answer, which is that I mean the big thing umbrella wise is electrification, right? So everyone wants to make every technology run by electricity. And the first question to research with that is should we do that? You know, should we make every single technology electrified? So there's a lot of research going on in modeling some of those processes, and I do some of that in deciding what systems are easier candidates to electrify. The big thing is electrified transportation. So, you know, most people hear about the electric cars, but in sort of the kind of less ready technologies, boats, planes, trains. So, you know, in our lab, we work on a project on electrified aviation for small, you know, the Cessna size planes with a company called Ampere that does this kind of work. And one of the big challenges for that too is that in traditional airplanes, for example, you have you can take the waste heat from the plane engine and send it to defrost the wings, but that waste heat isn't, you know, as strong in an electrified aircraft, and when the wings frost over too much, that's a huge safety concern. So those auxiliary challenges related to electrifying transportation. And then the other big thing is you know, AI, ML, and cryptocurrency is all, you know, whether we are fans of them or not, they're all taking, you know, significant power consumption with data centers, and so that, you know, data center cooling, the U.S. government has a whole program called Cooler Chips that's just how do we cool data centers. And many of these technologies want to be the sort of bubble pump-esque passive cooling, so in thermosiphons of these things. So it's all related to electrification and those kind of things. So first at the base level, what should we electrify and what should we do first? Then how do we manage these electrified technologies? And then, you know, with all of the development in renewable energy recently, we don't have as much development in actual thermal storage, and most of our renewable energy is intermittent. So it only comes on in the day, pretty much. Solar and wind both basically only work during the daytime, where many places have a strong energy demand at night, and a lot of it in HVAC. You know, 50% of most building energy consumption is in some form of climate. So all of those different challenges related to, you know, climate, electrification, and then how we adapt to those climate saving trends.
Yeah, that's a nice summary, Vivek, about nice themes about electrification and I mean, energy storage or addressing climate change. And wish you all the best in your career.
Thank you.
Yeah.
All right.
Thanks, guys. Thanks, JS, Vivek. So now this was the Father and the Son. Go have some Holy Spirit.
Okay. Thanks, guys.
Okay, thank you. Thank you.
Bye-bye.
JS, you